Hello, hello, hello. My name is Joseph Milliken with Source Allies. This year, once again, we are sponsoring Advent of Code. Ben did an amazing video on day 3. Great. Also did a great one for day 7. If you haven't seen either of those, you're missing out. Today, though, I'm here to do a video for Advent of Code day 14. Now, much like both Ben and Gray, I am a bit of a nerd, so usually I attempt these just as they're released, but just so I could share the experience with you, I have decided to be patient and not attempt it until now. So, without further ado, I have my code right here waiting for our problem. Let's jump straight into day 14. So, we have some words, lovely stories, we love the stories. And it looks like we have our first example, robots' current positions and velocities. So we're going to take that, probably going to need to parse it at some point. We'll figure that out in a second. So I assume these are going to move by their velocity, position of 0, 0, top left corner, velocity x, y. Yep. Okay, so they can move. There is a set width and height. Those are some interesting numbers. The example has a different width and height. Okay, that's going to make debugging a little easier. So visually... Okay, so there can be two robots on the same coordinate, and this number tells us how many are on that same coordinate. So on 0, 4, there are two robots, indicated by the 2. Okay, that's interesting. They can teleport... Oh, jeez. Wrapping around the edges. Okay, so we imagine the world is kind of like a sphere, or kind of wrapping around. Okay, it would have been really useful to use a robot that had like a velocity of 1, 1, but I can see it has a upward and to the right velocity, and it's disappearing and appearing down to here, and appearing over there. Okay, I can follow that. They wrap around both the right, left, top, and down edges. Simulate where the robots will be after 100 seconds. I can see that's our part 2, right? We're going to go for 1 billion. Okay, count the number of robots in each quadrant. Okay, so some math and counting, and then our result. And then, okay, I think I have all the information we need. So yeah, let's think of our plan. Usually I would whiteboard this out, but get a little bit more detail, but trying to be efficient time-wise here. So parse robot positions. I can't spell words correctly. And then so parse them, simulate movement for 100 cycles, count robots in each quad, return the sum, right? Do the sum of the product. That's all Advent of Code does with these. Multiplying them together. Okay, so those are our 4 things. So let's start with the parsing. In my mind, we have these lovely strings. Since we want a one-to-one representation of transforming these into other things, probably going to do a map. As we map through them, I'm going to go for an object approach. So I'm going to want x0, y4, velocity x3, velocity y minus 3. So const robots, data split, because we're given a string that has a bunch of lines. Then we take each line and we do our parsing. So we have our... So yeah, while these are 2 different values, they are the same structure. So if we split on space and then map over each of them, we can perform our parsing in one go. So we'll just say PV until we think of really cool names for it. We'll split on the space in our line and then map over each part because we're really creative for names. Now we want this stuff after the equals sign, so we'll split on the equal sign, let's say 1, and then since we're in 2 dimensions, but this would support 3 if we did get there, we'll split on the comma to give us the digits, well, the characters before and after the comma. Then for all of those, we will turn them into numbers by passing them or mapping them to the number constructor, which we can do like that. Now, if this works, we have essentially tuples of the numbers at the position and the numbers in the velocity. These are great. I don't want to deal with tuples. They're confusing. I always mix up the zeros and ones. So we're going to return our object with a position of a x, p0, y, p1. And you know what? Hindsight is 20/20. We could do something like that, actually. If I can spell the word velocity, that is. X, Vx, Y, Vy. Again, I'm going to keep our refactorings to a minimum for the sake of time. But this should give us a bunch of robots. which if you look at the first one, we will see position x, well, 0, 4, 3, negative 3. 0, 4, 3, negative 3. Parsing is done. It's a quarter of the way through. Let's simulate our movement now. So I call them cycles. What do they call them? Come on, where is it? Seconds, okay. For 100 seconds, for let s equal 0, s less than 100, s plus plus. For 100 seconds, the robots are gonna move. So, easiest way of doing this is going through each robot, adding to its x and y velocity. So for each robot of robots, robot position x plus equal robot velocity x, and we do the same thing for y. Which, if that was all we needed to do, we would be great. But unfortunately, that's going to make it fly off into space. So they have gone way down here, bottom left. They're off in another universe now. We need to do the wrapping around logic. So for the positive one, that's actually very easily. Well, very easily. It is very easy. We just use the old modulo operator. So if robot position x greater than or equal to, x would be a width. We don't have a width, of course, and that changes from our example to our real one, so we need a new parameter. Let's receive those new parameters. And let's pass them in for our example. I think it was 11 and 7. There was somewhere up here where they talked about, for this example, 11 wide, 7 tall. So 11 wide, 7 tall. And for our real one, it's 101 and 103? 101 wide, 103 tall. Okay, great. So we have that ready for when the real life happens. But now that we have our width, we can make sure, compare our widths. Once we go off our little grid, we wrap back around. We do that, again, with the modulo operator. Robot position x equals robot position x modulo width. Yes, there are better ways to do this. It could all be inlined, one-lined, fancy-lined. Going for maximum readability and quickest to implement, though. So that should wrap around the positives, but we're already being shown that that is not handling our negatives. So of the two walls that we have here, if I were to just take this really quickly, let's just TL draw it. Gross. We are handling wrapping around these two edges, but not these ones yet. So that's what we need to handle, which we will handle by checking if it's less than 0. If it's less than 0, the trick is to add the dimension that is the size to wrap around with, which in our case will be width and height. So if robot position x less than 0, robot position x plus equal height width, and then y for height. So this might be working. This might not be working. We won't know until we can actually look at it. That would require us writing visualizing code. Do we want to write visualizing code? Not unless we need to. So let's just assume we have moved them correctly, right? So now we need to count the robots in each quadrant. And that would require us to do some math. Yeah, so we could do some math here to figure out where their coordinate is, if it's within a quadrant, all that fun stuff. Or we could visualize it. I'm going to visualize it because that's going to be easier for me to validate if it's working or not. In the refactor, if I were doing a refactor, I would totally do a math-based solution. Probably would be faster, but let's keep it safe, not risk anything. So what I'm doing here is I'm building up a world. It's going to have it's going to be a 2D grid, so positions, and it's going to tell us how many robots are at that X, Y position. So for let x equals 0, x less than width, x plus plus, and then since these are just initializing, we can push an empty array of zeros here. A new array of height mini filled with zeros. We love that, and the world should look like this. I said it looks like this. Trust me, it looks like a grid of zeros. And then once we're done moving, we want to put the robots in the grid. So then I can visualize it, which will allow us to validate this code, and I can do quadrant counting in a way that I would be able to trust myself doing. So let's, for each robot, constant robot of robots, let's set the x and y. So robot, well, in the world, robot, not the web transport bidirectional string, robot position X, robot position Y. Yes, I know I could have encoded these as 1. That is not as easily to visualize as this. So if we look at the world, not the worldy, the world, we see we got a bunch of 1s and numbers, and this should visually match the grid that we have. I'm not seeing it, or the grid we're supposed to have. Let's look for this pattern. So let's look for a 1 and a 2 touching each other with a 1 diagonally offset, kind of. Here's a 1 and 2 touching each other. So I've messed up the orientation. In my mind, X and Y's had certain... There's a 1 and 2, and there's a 2 and 1. Everything is backwards. We love it. So let's just try things, use our eyes to validate. So if we go this way, and then we have to YX here, is this the system they were using? Lucky us. So I literally inverted it in my mind, but if we look here and we squint a little bit, we can see there's the 1, and then up 1 to the right 2, you got the 1 and the 2. So there's the 1, up 1, right 2, you got the 1 and you got the 2. So this not only validates that our movement is working, it's going to make the whole quadrant thing easier, because we're going to do some slicing to literally get a sub-matrix of this, and then just add up all the numbers. So let's work on that top left quadrant, since it should be the easiest. So const top left, world, slice, 0 to width. No. The first ones are y's, so it would be a height. I've spelled the word height correctly. So let's see what top left is now. Yes. So there were 7. We want... Oh, it's an odd number. Who gets the middle row? That's interesting. Who happens in the middle row? Oh, robots that are exactly in the middle don't count. So nobody gets the middle row. Okay, that's important. So this is the top, really. And if we want to get const top left, that would be top and mapping each row. Sure, yeah, the rows. Naming is all gone. Slice 0, height divide by 2. Now if we look at top left, okay, it's not vertically stacked no more, but it's 3 wide. No, it's supposed to be width. Okay, now it's 5 wide. 1, 2, 3, 4, 5, and 3 tall, and we have a 1 in the bottom left. And this is our bottom left. We have it. Okay, good. Let's go get top right. Top right is, again, we're going to map over top, but instead of slicing starting or ending at width minus divide by 2, we're going to start at width divide by 2. I might need to do some off by 1 stuff. This contains the middle row, right? I had to do off by 1 stuff. We're dealing with an odd number. So this isn't a whole number, isn't it? Mid X. Aha. So instead of doing that, so we do want this. What if we seal in this? Not CBRT, not C. Yeah, what if we seal in this and we use this instead? Will this just work? It works for that one. Let's do the same for height and make sure that everything loves that. So mid Y, height. Okay, great. Nothing broke. That broke. Okay, you know what? We're just not going to try to make that clean and pretty. For the sake of time, we'll just make it work. So we have that. For this one, we're just going to +1 it. There we go. Let's make sure top left is still looking good. Looks great. Top right looks great. Now we just need bottom. And I got a feeling that shortcut's probably going to bite me, but we're here, and they both appear to be odd length, so +1. Bottom, 3 rows, that's right. So top 1. Right, we have that middle one. We need to ignore that eventually. Okay, good. Let's let's just steal this code from up here, because this code works great. Just has the word top in it. Boop, 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 boop. Bottom. Okay, so bottom left, we just have the 1, 2, and the 1. Bottom right, we just have 1 and bottom left. We do. Okay, so that was a lot of manual effort. You know, we spent like 5 minutes to avoid 2 minutes of math probably, but I knew this would work. I was not that confident in my skills to math on the spot. So we have these quadrants. What we need to do is get their sums and then multiply their sums together. So const sums equals, so top left, top right, bottom left, bottom right. So for each of these, we're going to map over them. So this is a quadrant, and then we're going to flatten the quadrant. So we just have an array of numbers. And then once we have that array of numbers, we can just add them all up. So reduce sum, robot count. I missed all my parentheses, so let's put that, nope, put that there, get rid of that, put that one back, sum, robot count, initialize at 0 just to be safe, call it sum. And now we should have the, not the SVG number list, 1341. 1341, okay, we are nearly there. Nothing can stop us now, I said. Count the robots in each quad, return multiplied results together. That's just multiplying all the sums. So sums reduce total, sum, total multiplied by sum. Start at 1 because don't want to multiply anything by 0. 12 does not equal to true. I have failed to properly set up my test case, but it is 12, and it's broken. Have I put my input in? No, I have not. Okay, let's fix that. Let's grab our input, shove it in here, make sure I pasted it correctly. It looks correct to me. Okay. And we have a number. Number. Are you the number? Let's find. Okay, we are good. Let's keep rolling straight on into part 2. Oh, that's so short, part 2. A picture of a Christmas tree. What is the fewest number of seconds that must elapse for the robots to display the Easter egg, which is the picture of a Christmas tree? Okay, so this is hard for a variety of reasons. Reason number 1, we don't have an additional example. So we need to test this literally against our real thing. Fortunately, it gets easier because we either will or we will not see a Christmas tree with our eyeballs. Okay, so what we need to do for this is determine our success criteria. So what is a picture of a Christmas tree? Specifically a picture of an ASCII Christmas tree, because we can't, there's no PNGs here. So as I think about that, I'm going to copy my function for part 2, because there will be modifications. And I guess I'm ditching the example, because there's nothing to example. And yeah, 2 parameters, 101, 103. Our heights and stuff don't change. I lost a curly brace. Yeah, so that happens. We're not counting things in quadrants, so let's just clean up what we can. We're not doing that, right? So we are moving, not for 100 seconds, until we find a Christmas tree. So this is a while loop. I'll put false in here for safety purposes. Please save. Okay, I've ruined all my parentheses. That's all right. So we need to keep doing this until we see a Christmas tree. Let's define a Christmas tree. ASCII Christmas tree. Okay, I don't know why I needed to Google this to see it. This is probably more realistic to what we're going to get. So it's a bunch of robots in a tight pattern. Okay, so one approach I could do is I could find a bunch of robots and be like, hey, are you all touching each other? Are you touching each other in a giant group? You might be a Christmas tree. We can also go for the base. Because even a hollow Christmas tree, they all have this base here. So if we detect a continuous line of robots that's like a big line, then we can think that's the base of a Christmas tree and perhaps just dump the output for our eyeballs to see. I like that idea, mainly because I can't think of any other ideas at the moment. So we're going to, it's going to need to be doing 2 things. So for every iteration, we will actually need the second here. So this does need to be a for loop. For let s equals 0, 0 or 1, because at this point we might hit ourselves with an off by 1 error if we do this wrong. After 1 second. If it's off by 1, it'll be fine. False s++. So this is just saying run forever once I turn it to true. So we move our robot, and then we need to, I think we're going to paint a world again. So hey, this visualization code coming in use again. So I'm glad I didn't do math, because I wouldn't have had this to work with. So what we want to do is we want to put the robots on the world and then run a line detection algorithm function on the world itself. But then we want to remove the robots from the world and put the robots in their new position in the world. But make sure to remove them before they move Let's increment, decrement. Let's not do that. Let's just make a new copy of the world, right? Let's say memory be darned. And we say const current world, and we use the most efficient way to copy a data structure deeply. I'm being sarcastic, for those who couldn't see that. It's the laziest way. We turn it into a string, and then we turn it back into its data structure, JSON stringify, JSON parse. So now that we have ourselves a world, well, at least be somewhat good. Once the robots have moved, so we don't need the world there, we need the world here, we put the robots on the world. And then we look at the world for a really long line of robots. So we already have putting robots on the world code. I just got rid of it. Here's putting robots on the world. Right here. Right there. Yeah, I'm fine having another loop down here. Separation, responsibility. That code just moves them. This one paints them. Not the big world, the current world. Okay, so the robots are on the world. If I were to put a return and set this to true, the real true, not that, we could see the current world if our code was running. Hey, I'm using all syntax wrong. Look at that. It's a world of robots. There are some ones in there. It's a really big grid. We can't debug in the 7x11 anymore, so it's going to be a little tough to visualize in here. I have to start writing to a file. Okay, so we have a world. We need now to write a little function that says, hey, is there a line of robots? Very common function. Probably could import for some cool library. But we'll implement our own. Has a line of length. So this is a world number, length, because this might change. We'll start off with this number. And the way I'm going to do this, the idea is to loop through every position on the grid, again, very efficiently. And then for every position, if it is a positive value, look in every cardinal direction, north, east, west, south, and then move length a number of times for each time we move, checking if that is a positive value. If all of them are positive, congratulations, we did it. Otherwise, failure, move on with your life. So for, right, and it's not a row column, it's an XY, and it's not an XY, it's a YX, so la la. So y of world.length, let's copy that for the x, put our missing things in here, boop, make sure we handle the rectangulars. Now technically x and y don't matter here, but we're here. Now we need to check if we even want to start here. So checking if world yx, since we're dealing with numbers, we can just use the truthiness. So if not world yx, continue, ignore it, we don't want to look at it. Otherwise, there might be a line here. So for const y offset, x offset of directions, cardinal directions, which I haven't defined yet, because I will do so right now. Cardinal directions. I will not be doing these in any particular order. I'm just going to define them all. Again, usually I'd clean this up a bit. Great comments, but we are just moving along. Okay, for all our cardinal directions, north, south, east, and west, they're in there. This one's north, this one's south, this one's west, this one's east. Or east and west, I don't know, I mixed them. So once we have a direction, we want to detect if there is a line here. And then if it is or isn't, well, if it is, then return true from the whole thing. If it isn't, return continue, rather. This sounds like another tiny little function for me. Function is line at world number, row, y number, x number, length number. I'm doing this because I can see me setting a flag, changing the flag, and breaking a for loop. Whenever you feel that pattern coming on, it's easier to make it a function. So we're assuming that one's already there. Let's just do it for each one. So for let o equals 0, o less than length. We could have an off by 1 here, but we'll test it. And then we need the new x and the new y. So nx and y equals x plus, and then we need x velocity and y velocity. X or x offset and y offset, whichever you go with. X plus x offset times whatever part of the line segment you're on. So that is our normal offset. And then it's y plus y offset times how many times we're on this line. If world in y, I've ordered them x and y again because that's the way my brain likes it, but we're doing yx. I'm doing it because the moment I don't do it, something's gonna go wrong. So if this conditionally, because we could be off the world. No, we can't. We have to wrap around. Math. Okay, I'll get that in a moment. If it is not truthy, which means we are off the world, return false. Doesn't mean we're off the world, it means the line has ended, has not satisfied our length. Otherwise, we were able to go through all of them were there, it's true. Yes, I can get functional, I can use .sum, I can use .every. This is what I'm going with because this is the shortest to implement. Now we need wraparound logic, which is going to be easily for the modulo, but then mathematically we'll need to do stuff for the negative. So let's make another tiny little helper. We need all the help we can get. Wrap around number, and what we could define minimum and maximum, but the minimum is 0, so we're going to keep this as simple as possible. The maximum is what we need to wrap around, and then the value is what needs to do the wrapping around. Let's start with the easy one. If value greater than or equal to max, just return value modulo the max. Else, if value less than 0, sorry, I'm writing code in different order. So if value is less than 0, then we need to return. It's the same thing we did for our robot moving. We add the dimensionality to the value, and that will do the trick. The dimensionality is max, so value plus max. Okay, so yeah, if you're too far, if you're too big, then we'll modulo you down. If you're too small, we'll add you up. If you're just right Goldilocks, we'll just return you as you are. Perfect. So we wrote this cool function so we could use it here on the scary math bits here. All we need to provide to this is a max. So y is world.length, and x is, thankfully these are rectangles, so it is world0.length. Okay, so we just wrote a lot of code there. Let's finish up this function, and then we can start testing for validity. So that will be if is line at, so we're passing out the world, our y, our x, our y offset, our x offset, and our length, which is from our parent. So if we found him, return true. Yeah, that is this function. Does it work? Well, we could throw it in our code, but I need to have confidence in this. So it has a line of length. We're going to define a world here, 0, 0, 0, 0, 0. So it's a 5 by 5 world. It's very amazing. And then we're going to have a length of 2. Undefined. Hey, when you fail, return false. That's why you test your code. So there are no lines of length 2. That's right. Put a 1 here and a 1 here, though. We have a line of length 2. Okay, what about a line of length 3? Okay, so it looks like we don't have any off by 1s. Lucky us. Okay, now what about a line of length 4, but you wrap around? Okay, so we can wrap around positive. Let's make sure we can wrap around. A negative wraparound will be the same as a positive wraparound due to the inefficiency of we're just checking everything, so that doesn't matter. Let's make sure we can wrap downwards, though, or in the other axis. So drop these to zeros, drop these to zeros, drop this to 1, drop this to 1, and one more 1. It's working. Okay, I have 90% confidence that this does what we want it to do. Does it do it fast enough, though? I got no confidence there. Now, the next thing we need to do is, we don't know how big this Christmas tree is. If we look at ASCII Christmas trees, like how big, I don't want to go there, I don't know your website, right? Like it can't be 3, because that would be the smallest tree ever. It wouldn't be able to get any tree shapeness. So I say let's go big, and then let's go down with it. That would also depend on how many seconds we want to do. We don't want to go infinite. My computer would not like that. Let's go 10,000. 10,000 feels like a good number. So let's check if has line of length. So our current world, let's pick a length. If it's 100 by 100, 90 is too big. 5 I think is too small. Let's literally do 50. And then console log, what do we have? S, right? Let's get rid of this return. This is where I probably will need to drop out of Quokka for runtime reasons. What happened to all my curlies? Let's fix this. Let's say const possibles is this, and we'll push it to possibles. Possibles a push current world for const w of current, not cursor to, current, not create secure context of possibles. Sorry, my brain. I also need to push the second. Fine, we'll push s and current world, s world console log. S world. I'm not going to be able to see the world. Okay, I think we just need to start running this. TSX solve. Yep, I'm going to turn off Quokka. I expected that to fail. Run it for real. It would help if we knew, okay, so hey, that ran pretty quick. So either it's 50 is too big or 10,000 is too small. Let's go down to 10. Okay, that's a number. Look, it's a Christmas tree. Ah, I can't see it. Okay, so we have a potentiality. What do we do with this potentiality? We need to look at it with our eyeballs. We cannot look at it like this with our eyeballs. We need to look at it. I think we'll have to write this to a file, or we could try and console log it. I'll try and console log it. I don't think 100 is going to fit in the old terminal. It will. I don't think it's going to fit neatly in the terminal. So for row.join this. Before we do joining on that, the number of zeros, I've done this before, will hurt your eyeballs. So if C equals 0, put my symbols back. Let's go with a space, because terminal's a monospace, it's fine. Otherwise, go with a C join by this, and then join our lines by new lines. And yeah, types are angry because everything is angry. Don't worry about it. Oh, this also isn't going to look good on a 24 font screen. I didn't think about that. Yeah, this looks horrible. That's awfully Christmas tree looking. It takes like 3 pages, but that's a Christmas tree. Okay, what's our thing? 6474. Let's go for it. No. So I'm probably gonna get timed out a little bit. So the thought that just hit me was, remember when I said like, we'll worry about the off by 1 once we actually, get the thing visualizing. I bet this is it. So it's not 6474, it's 6475. Now, I think the timeout was 1 minute, so I might still have to wait a little bit. Okay, 20 seconds left to wait. Assuming this has all worked, then this is it. We have moved the robots, and we have detected a Christmas tree by looking for a line of length 10. Kind of lucked out just with the number here. Could have been more, could have been less if I look at it with my eyeballs. We could have went for many lines, because I was assuming a hollow Christmas tree, but this makes it easier. We have 1, 2, 3, 4. That looks like more than 10. Plus, we have the verticality and all these things. Also could have looked for a box, but we didn't know we would be looking for a box. That's the fun part of you only get so many requirements. And it is working. We have gotten our historian through the robot security. Okay, so this is done. Usually I would, refactor this a little bit more, go through it some more, but I believe and I hope that I sufficiently explained the process as I actually wrote the code. This could have been done with math. Probably more efficient to do it with math. Maybe even more understandable to do it with math. I knew I could get it working by slicing in a sufficient amount of time. Doing it with math would have been a risk in time. Same for what we're doing here. We're effectively, this feels like a brute force solution. We're just going through it and waiting for a Christmas tree to appear. There are probably patterns to how the robots move that you can do some cycle detection or some kind of observation, and then with that observation, do really cool math to immediately jump to this position of where the Christmas tree shows up. There might even be some other things like robots never overlapping. That could be a condition for the Christmas tree appearing. Lots of other different ways of doing this, but this is the way I came up with, and it worked, and it works under like 10 seconds. So that's like more than a success in my book. But with that, both problems are solved, and we are done. So, thank you for joining me on this adventure, helping our historian avoid security robots in our Advent of Code Day 14. One of my favorite parts of Advent of Code is seeing all the different approaches to solve a single problem, because you would have never thought of all the different ways there are to see it. So, this has been Joseph Milliken with Source Allies. Got a topic you want to see covered, or you just want to share some insights or maybe your solution or approaches to this particular challenge? Put them in the comments right down there below. And if you're just a touch curious about us, I'm personally inviting you to come on over to our corner of the internet at sourceallies.com to see what we're all about. Have a good one.